Let's solve now problem 38 in page 92 from Siegel's biochemical calculation. It's a long problem. I'm going to do that in parts. This segment will do part A. All these problems ask you to describe the preparation of 40 liters of a 0.02 molar phosphate buffer solution, pH 6.9. In A, we are starting with 2 molar phosphoric acid solution and the 1 molar KOH solution. That's for A that we start now, and the other problems are going to refer to this one, so I don't have to be repeating the same thing again. So 2 molar phosphoric acid and 1 molar KOH. So when we deal with a problem like that, the first thing we'll write the 3 reactions, because we have here the 3 pKa's, pKa 1, 2.12, pKa 2, 7.21, and the pKa 3, 12.32. 12.32. So this from the table or from a data bank in a test, and we know that we are closest to the pKa 2. So we know that this has 3 dissociations. This is a polyprotic acid. We discussed that in classes. H3PO4 dissociating H plus and H2PO4 minus. That's the first Ka or pKa1, and then H2PO4 minus is going to dissociate in H plus and HPO4 2 minus, Ka2. That's the one that we are interested in, right? Because that's the one that's closest to the pH that we are working. So the pH for this buffer is going to be pKa, Henderson-Hausenberg equation, log of the concentration of HPO4 2 minus over the concentration of H2PO4 minus. We know that's the conjugate base over the concentration of the acid. However, in a polyprotic acid, it's always convenient to write the equation so that you know exactly which species you are talking about. Moving up a little bit here and plugging the numbers, we know the pH that was 6.9. We know that pKa 7.21, so we have a log of the concentration of HPO4 2 minus over the concentration of H2PO4 minus. Now we know the ratio based on the antilog in here. We can rearrange the numerical to the same side so that it is going to give us HPO4 2 minus divided by concentration of H2PO4 minus equal 10 to the power of negative 0.31. Yeah, that's 6.9 minus 2.71 is 0.31. Okay. And this gives 0.49. So the concentration of HPO4 2 minus equals 0.49 the concentration of H2PO4 minus. We have another equation that you know for this buffer here, that the concentration of HPO4 2 minus and the concentration of H2PO4 minus is going to be 0.02 because that's the buffer that we have. We have a 0.02 buffer solution, okay? Now we have 2 equations, 2 unknown. We can find out what they are. So we have here 0.49 H2PO4 is the same thing as HPO4 2 minus, right? So plug in the numbers here, plus concentration of H2PO4 minus equals 0.02. In other words, 1.49 concentration of H2PO4 minus equals 0.02. Run out of space here, sorry. 0.02. So from that, we can calculate the concentration of H2PO4 minus, which 0.0134 molar, and the concentration of HPO4 2 minus can be also determined here by the direct calculation. So HPO4 2 minus means 0.0066 molar. This is going to be very important. These two concentrations here are going to be very important for the next series of problems. I'm going to refer to that all the time so you can come back here and find out all those concentrations. Okay, so these two, the concentration of the two species, the acid and the conjugate base, is going to be important for the other problems. So we know that this phosphoric acid is the only source of phosphate in here. So we can calculate how much phosphate we need based on a dilution, because we are starting with a solution that is 2 molar, and we want to make it 0.02 molar. So basically a dilution, 2 molar, what volume we need from that 2 molar solution equals 0.02 times 4, that's the final volume of the buffer. We want to prepare 40 liters. So therefore we need 0.4 liters or 400 milliliters of the phosphoric acid that's available as a 2 molar solution. Okay, so that's first part of the problem. And you can do that without knowing the specific concentration of each one, because phosphate all come from phosphoric acid. Now what KOH is going to do is that pick up this phosphoric acid and force it to dissociate, to remove protons from this H3PO4. First, it's going to remove protons to generate H2PO4 minus, and then more hydroxide is going to be added to remove protons from the H2PO4 minus to generate HPO4 2 minus. Okay, so first we have phosphoric acid, and the number of moles that we have of phosphoric acid can be calculated by the relationship here. The number of moles is going to be 0.02 times the volume of the solution, right? So we have basically in this buffer we have 0.08 moles, or 0.8 better saying, 0.8 mole of phosphoric acid that has been added to that solution, and then now KOH is going to remove from those phosphoric acid, and remove protons from them. So we have 0.1 mole of KOH is required to remove all the protons from the first protons and generate from H3PO4 going to be generate H2PO4 minus, right? So they need 0.8 moles for that. Now let's calculate how many moles we need the KOH to do the additional job that's needed. In other words, to take from H2PO4 and now generate HPO4 2 minus. All right? So that's additional amount of KOH that we need. We know that from the calculation before that we need to generate 0.0066 molar in 40 liters of HPO4 2 minus. So we know the number of the HPO4 2 minus species that we need. So the number of moles of the HPO5 species that we need is calculated by the relationship of molarity equals number of moles over volume in liter. Therefore, 0.0066 times 4 is going to give us the number of moles that we need for that. And that number of moles is 0.264 moles of KOH. It's actually HPO4 2 minus, but also the number of moles that the KOH that we need. That's 0.264 mole of KOH. This KOH is going to take H2PO4 and carries it to HPO4 2 minus. So the total, let's get more space in here. The total is KOH, the total of KOH is going to be 0.8 that we need initially to remove the first proton, 0.8, plus 0.264 that we need to remove the second proton for some of this species, right? Not the entire species. So that generates a buffer. This combination here gives 1.064 mole. So the KOH is 1 molar. KOH available is 1 molar. We need 1.064 moles, so we can calculate the volume that's needed for that buffer. So again, the same relationship. You can calculate the number of moles multiplying the molarity times the volume in liter. So the volume in liter here also is calculated by normal number of moles divided by the molarity. 1.064 divided by 1. Don't need calculator for that one. Is 1.064 liter. Sorry, this should be liter here. 1.0464 liter or 1064 milliliter.